Hey everyone, my name is Sin, and my talk will be on solving tracking problems with Stone Soup. So a little bit about myself. I'm a backend software engineer for a government contractor, and that's pretty much all I can say because I signed an NDA, and you don't want to be on the bad side of the US government. So my talk will be on solving tracking problems with Stone Soup. But before we get into the code walkthrough, I'll go over a popular filter called the Kalman filter. So brace yourself because there's going to be a lot of math. Also, some of the words that I use might not make sense initially, but hopefully as the talk continues, it'll be clearer to you. So this is the roadmap for this talk. We'll start off with an intro to Kalman filters. We'll look at the intuition and the math behind Kalman filters. Then we'll look at Stone Soup, the code walkthrough, and if there's time left, Q&A. All right. So the Kalman filter is a temporal iterative stochastic process. And I know that's a lot of words, so let's try to break it down. The Kalman filter is temporal because we're modeling the evolution of a state over time. And it's iterative because it operates recursively. In order to make a new estimate of our state at each new time step, we use a prior estimate and fuse it with incoming measurements from our sensors. And it's stochastic because it deals with uncertainty. The Kalman filter was invented in the 60s by Rudolf Kalman as a way to estimate linear systems with noisy data. And it has several different use cases from signal processing to predicting time series data in finance. The Kalman filter is essentially a weighted average of noisy measurements. There's some unknown value that we're interested in. Unfortunately, we don't know the true value, but we have sensors that give us estimates, and we combine these estimates to produce a better approximation. So here's an example using a signal processing example. Here we're trying to estimate the position of an object using noisy measurements from two different sensors, a GPS sensor and an IMU. And let's say that the GPS provides accurate but infrequent position updates, while the IMU provides frequent but noisier measurements. We might think the GPS would be a better estimator since it provides accurate measurements, but the Kalman filter is an equal opportunist. So we'd include the measurements from both sensors because they contain useful information. The Kalman filter reviews both measurements to produce a more accurate and reliable estimation of the object's position. So the end goal for the Kalman filter is to produce an optimal estimator. And remember, this optimal estimator is essentially a weighted average. The weight given to each device's measurement is proportional to the confidence we have in that device. So going back to our example, the GPS would have a higher weight than the IMU since we have more confidence in that device's measurement. And the confidence we have in a particular device is modeled using covariances. And as a refresher, the covariance looks at the relationship between two random variables. It's essentially the unnormalized version of the correlation. And if you remember, the correlation is the covariance divided by the product of the standard deviation of X and the standard deviation of Y. That's a lot of mumbo jumbo. Basically, we're saying that when you hear the covariance, think of variability. The smaller the covariance, the less variability we have. The larger the covariance, the more variability and uncertainty we have. So there's this inverse relationship, which is why having a smaller covariance is linked to having a higher confidence. And the device that produces the measurements, like the GPS sensor or the IMU, are modeled as continuous random variables. As another refresher, a random variable is a variable that can have multiple possible values. So it has the possibility of taking on this value or the possibility of taking on another value. A very popular example is rolling a six-sided die. The random variable would be represented as a set or a tuple with the values 1, 2, 3, 4, 5, and 6, because our die could land on any of those values. So how does the Kalman filter choose the weights for each sensor? Weights, also known as the Kalman gain, are chosen to minimize the mean squared error between the prior estimate and the incoming measurements at each step. And this is done iteratively, which is great for us since we usually don't know the initial state of the system, nor do we know the control inputs. And since we don't know the initial state, there's a chance that our initial assumption could be way off, which could lead to like an egregious divergence from the true state, which is really bad. So to avoid this nightmare, we incorporate incoming measurements at each time step. And here is a quick snapshot of how the Kalman filter works. We start with our initial assumption, and then we have these two steps, the prediction step and the update step, and we loop between these two as new measurements come in. So with the prediction step, we start with an initial state. At each time step, we get an approximation of the state at time t using prior information from t-1, and we call this the a priori estimate. And then for the update step, sometimes called the correction, we use the a priori estimate and we fuse it with incoming measurement data taken at time t. And this creates the a posteriori estimate. I hope I'm saying this right. My Latin is not that good. So the a posteriori is used by the Kalman filter to produce the prior estimate for the next increment of time. And this is a great visual of what's going on with the Kalman filter. So we start off with our initial assumptions. Next, we find the Kalman gain, which are the optimal weights chosen to minimize the mean squared error. And you can think of this as like a trust gauge. It decides how much trust we have in the new sensor data. We then make a new guess that combines our original estimate and incoming sensor measurements. So this is that step here to get closer to the truth. Next, we update our confidence. Next, we update how confident we are about this new guess, which is this step here. And then lastly, we have a new and improved guess we use to make predictions about what we'll see next, like guessing where an airplane or a car will be in a few seconds. This process repeats itself at each new time step. Overall, the Kalman filter is making better guesses each time by mixing prior estimates with incoming information. And this slide is another diagram of how the Kalman filter works. It's the same information presented in a slightly different way, and we'll actually see these equations again. So so here's Stone Soup, and this QR code takes you to the documentation for Stone Soup. And Stone Soup is a framework for developing and testing state estimation and tracking algorithms. So now let's move on to the walkthrough. Hopefully you can see this, and I'll be zooming in too. So here we have the code that I want to walk through. So I'm using TragAir, which is a set of decoded ADSB messages, and ADSB is short for Automatic Dependent Surveillance Broadcast. It's basically surveillance data for aircrafts or other airborne vehicles like drones. And this data was collected by the Air Lab, which is a research team from the Robotics Institute at Carnegie Mellon. And it has a lot of great information when you are trying to create a tracker, things like latitude, longitude, altitude, a lot of great stuff. So the first 13 columns were a part of the original data set. This third one, I thought I needed a geometry column, but I didn't. So here I'm just loading in the data. But now we're getting into creating our actual tracker. So how do we make a tracker? We need these several different components. We need detections, which are essentially measurements, predictors, updaters, data associators, hypothesizers, initiators, and deleters. And we'll go through what each of these different objects does. But once we have all these components, we can create and run our tracker. So we'll start with what a state is. A state vector is a representation of the state of a system at any given point in time. So in this demo or in this walkthrough, we're interested in the latitude and longitude of an aircraft. And this can be represented as this vector here, where x is our latitude, y is our longitude, x dot is the change in latitude, and y dot is the change in longitude. I'm not sure if I mixed up my variables, but if I did, I'm pretty sure you got the drift. So Stone Soup's state vector is a wrapper for NumPy arrays. Next, we have a detection, which is another way of saying measurement. And these observations are generated from a sensor. So going back to our example with the GPS sensor, it would produce these measurements. And a detection requires a state vector. So here I'm creating a pandas reader, which takes in a pandas data frame, and each row will be converted into, or will be used to create a state vector. So here is the line where we create our state vector. We're only interested in the latitude and the longitude. And there is some other information that's useful too, like the ID and tail and speed and altitude and whatnot. But we don't want to add it into our state vector, so we can just add it as metadata. All right, so next up is a predictor object, and this is used to predict a new state given a prior state and a transition model. And transition models are sometimes referred to as motion models. So here we're using a constant velocity model as our transition model, since aircrafts usually maintain a certain speed, heading, and altitude while in flight. And this uniform motion can be modeled using constant velocity. There are other models to choose from too. So here's the math or the equation to that. And I want to go into what this means. But first I'll say we can ignore G and U because these are control inputs. So G is the control matrix and U is the control vector. Sometimes we don't know it, so in Stone Soup this is optional. What's really important is this here. So F is our transition model or motion model. And it's important because this simulates how the movement of our object, it simulates the movement of the object that we want to track. And we right multiply it with the prior state. So x hat is what we're trying to estimate since we don't know what x is. And we use the prior state and the transition model to get our prediction. Cool. So then next up we have the updater object. The updater object is used to update the predicted state. It uses a measurement and a measurement model, and there's several different processes that are being computed during this part here. I won't go into all of it in detail, but we'll start off with the Kalman gain. And this is the equation for the Kalman gain. I'm not going to go into the math for that. We just know that K is the Kalman gain, P is the predicted error covariance, H is the observation matrix, and R is the measurement noise covariance matrix. I will say, though, that H is very important. It measures what we observe in our state vector. So sometimes there are hidden states, for example, angular velocities like pitch rate. We probably don't have a sensor, or maybe the data is corrupted. So that would be considered a hidden state. What we can see, or what we can observe, would be this matrix H multiplied by a state. Next up is the update estimate. And I will actually go into what this equation does. Just remember that Z is our incoming measurement from a sensor. So here, we start with the prediction of our state that we calculated earlier, so up here. And then we add this term to it. So starting with the parentheses, this difference here is called the innovation. And the innovation measures the divergence between the actual measurements and the predicted measurements. So what's coming in from a GPS sensor subtracted from what we predicted. And then we multiply this by the Kalman gain, and this minimizes the innovation, which results in a smaller covariance matrix and increases our confidence of that state estimate. So overall, this is how we incorporate new measurements to update our predicted state. And remember, this is the a posteriori. And then lastly, we have the update covariance. I'm not going to go into that equation. Just know that I is the identity matrix and P is used for finding the Kalman gain. So here in these three blocks, I am defining the transition model. Remember, we're looking at latitude and longitude, and we're using the constant velocity motion model. And then I'm defining the measurement model and using those two to create the predictor and updater. Next up, we have the hypothesizer object, which uses a track and a set of detections to produce a hypothesis of association. So what does that mean? The hypothesizer answers the question, what is the likelihood that this detection is a part of this track? And a track is a group of observations that are related. So an example would be observations related to an aircraft with a particular ID. So our hypothesizer is going to look at a detection and see whether or not it is supposed to, or if it belongs to a particular track. So here, I defined my own hypothesizer because I was getting issues with Stone Soup's hypothesizer. Like my state vector, for whatever reason, wasn't a one-dimensional array, but like, let me just scroll up. Because I'm pretty sure this is a one-dimensional array, right? This is a one-dimensional NumPy array. I'm not crazy, right? So for whatever reason, Stone Soup was just being really finicky, so I had to create my own. And then here I am using the ravel function to, I guess, convert those state vectors into a one-dimensional NumPy array. And then I'm using SciSpatial, the Mahalanobis distance, to calculate the distance between those two state vectors. But Stone Soup does have the same thing. I just couldn't get it to work for me for whatever reason. Okay, cool. So next we have a data associator. With this object associates tracks and detections, and it requires a hypothesizer. So recall, we're using the Mahalanobis distance to compute the likelihood of a detection being associated with a track. Next up, we have the initiator object, and this takes detections and uses them to create new tracks. It estimates the initial state of an aircraft based on the detection. It also ignores false alarm detections. So that's the initiator. And lastly, we have a deleter object, which identifies tracks for deletions. Without this, a system might be cluttered with outdated or false tracks, which could be computationally expensive and produce low-quality results. So in this walkthrough, our deleter will delete tracks if they haven't been updated for 10 minutes. Great. So once we have all those different components, we combine them to create a tracker. And firstly, the tracker calls the data associator on any active tracks. Tracks are updated if a detection is associated. If the detection is a dud, the tracker leaves it as a prediction. Next, tracks are checked for deletion. And then finally, the initiator will use any remaining unassociated detections to create new tracks. And so here, we're using the multi-target tracker because our data set has multiple aircrafts, and we want to track multiple targets at the same time. All right, so that's it. No complex math formulas to remember. Stone Soup is like Build-A-Bear for trackers. So you could mix and match different components if you wanted to. So for example, instead of using Mahalanobis, you probably could have used a Euclidean distance, or instead of using constant velocity, you could have used constant acceleration, or a mixture of the different motion models, which is really fun. Yeah, and there's other things that you can mix and match too. And that's the walkthrough for creating a tracker. And I said that I'd show you how to create a tracker. I didn't say it had to be a good tracker. So this tracker is very slow. I was trying to plot the data that I did get, which gave me a whole bunch of duplicates. So in blue is the ground truth, and then this single red dot is from the tracker. But now you know how to create a tracker using Stone Soup. And Stone Soup also does have a plotter class that allows you to plot changes in your tracker over time. So if you happen to create a tracker and use it for any plotting functions, I'd love to check it out. And if you're a tech-savvy stan and want to track your favorite celebrity's private jet, now you can. Although I don't encourage stalking celebrities. All right, so thanks for listening to my talk. I have this newsletter here that's relatively new, and I'll be posting a more refined version of the Jupyter Notebook, along with a couple papers I read that helped me understand the Kalman filter. Eventually, I'll post other things related to geospatial open source software. And there's also my LinkedIn if you want to get in touch via social media. And there's plenty of time for questions, a lot of time, OMG.
Thank you. I have to say, I think the most universal experience is I tried using this thing that existed. It didn't do what I wanted, so I just built my own.
Yeah.
I love that. Okay, a few questions from the Slido. And pardon me if I'm going to try and make... I'm learning the context here. Have you tried using KF, I assume Kalman filters, for fraud detection patterns with behavior time series data? And if not, what other MSE or algorithm would you recommend?
Could you repeat the question?
Yes, I will try. Have you tried using Kalman filters for fraud detection patterns with behavior time series data?
So I've only used Kalman filters for sensor fusion. I can't really say much, but just imagine that you're trying to track a bad guy in an airplane.
All right.
Yeah.
Enough said. Are there any alternatives to the Stone Soup framework that you considered using? And if so, what made Stone Soup the best option?
So there is PyFilter. That's another class or another package that you could use to create, I guess, trackers using Kalman filters. But it only has, I guess, code for creating Kalman filters. Stone Soup has so much more going on besides using Kalman filters. You can use other filters as well. And you can import different types of data. So you can import video data, CSVs, Kafka, a plethora of different things. I feel like Stone Soup just has more for you if you're interested in going that route than PyFilter.
Okay. Someone asked the name of the Tony Lacey book that you cited.
Oh, Tony Lacey. I can go back to that slide. It's not a book. It's like notes. So if you type in Tony Lacey Chapter 11 tutorial, you'll see it. It's probably the first or second link on Google.
Okay, cool. How do you choose the model to use for your data when it's not obvious which might work best? And is there a best fit method?
Yeah, that's why you need to explore different models and see which one works for you. I've only ever used the regular Kalman filter. There's like the unscented Kalman filter and some other stuff too. But I think it depends on your level of comfort. I start with the Kalman filter because it's the most simplest one. Hopefully it's simple. I know these equations are kind of complicated looking.
Yeah, I define simple differently, but if it makes sense for you. Is it safe to infer that Kalman filters work like ML models?
Oh, that's a good question. I'm not sure. I am not a machine learning engineer. I'm just a backend engineer, so I don't know if I can answer that question.
Okay. What are some assumptions of the Kalman filter, particularly with respect to statistical properties of input data? That's a hard one.
So this one in particular is expecting that your system is linear. And also when you're calculating the, let me go back to the Mahalanobis stuff. So when you're finding the inverse of the covariance matrix, it has to be, what's it called? It has to be a square matrix, and dang, the term is like losing. It's not coming to me, but I'll get back to you. Whoever asked that question, just reach out to me, and I'll get back to you because I'm blanking right now.
All right, that's what Discord's for, right? We've got the Discord. Awesome. That was the last of our questions. Thank you so much for that. I appreciate it, everyone. Help me thank Cynthia.